There is one still waiting.
One person, yeah.
And now the meeting is recording.
Okay, so there's one people waiting still in the waiting room. Is one person there?
Is joining.
Deep Lab Pal.
Everything is joining.
We can also manually admit.
Okay, I will admit him manually.
Yeah.
Okay, that's I'm doing now. Okay, I think we can start now. Carmine, what do you say?
Yeah, we are perfectly on time.
Okay, right. Yeah, we are right on time. So welcome everyone to this session, this mini-colloquium on spin transport via geometric design at nanoscale. My name is Diego Frustaglia. I'm organizing this together with Carmine Ortiz. You can see him there on the screen. We have several talks today, 2 invited talks, and 1, 2, 3, 4, 5, 6 contributing talks. And okay, let me see. We have 2 sessions, one today and one tomorrow. The rules regarding the questions is, in principle, you should share them in the chat. Yes, but there's some people who will admit questions in the middle of the talk. I think Klaus agree with that, right? And I don't know, Yusaku, if you prefer questions in the end or in the middle of the talk.
14 minutes, it's very strict. I don't know. I can finish within 14 minutes if.
Okay, good. So let's ask in the end. For Yusaku, please send the questions to the chat, and we'll read them in the end. So in principle, you have Yusaku, 30 minutes plus 10 for questions, the same Klaus, and the rest is 15 minutes plus 5-minute questions. Yeah. So let's try to stick to the plan. And Yusaku, you can start, please.
Yeah.
So the first talk is by Yusaku Nita. The talk is spin interference control by geometric effect, and he's from Tohoku University in Sendai, Japan. Please, Yusaku.
Yeah, thank you very much for your kind introduction, Diego. And it's my great pleasure to join this the colloquium, and it's also a great pleasure to meet the audience. And so this is the title of my talk today. I will discuss spin interference, which is controlled by a geometric effect. And this is the content of my talk today. At the end, I will mainly focus on geometric effects, which assist topological transition in spin interferometer. So actually, this is a collaborative work with my colleague at the Tohoku University, and theoretical support was given by the group of Diego at the Sevilla University. And the numerical calculation was done by Henry Sarkowski when he was at RIKEN. So as you may know, the origin of the spin-orbit interaction is not magnetic field, but the electric field is rather important. So this is a very, very tiny magnetic moment of the electron spin. So this magnetic moment is very easily coupled with magnetic fields shown here. So if you look at the spin-orbit interaction shown here, so you can find that this guy in this bracket should correspond to something like an effective magnetic field. The most important parameter for the spin-orbit interaction is not magnetic field, but the electric field is rather important. So when electron travel in this electric field, the electron can feel the effective magnetic field, and which is also momentum dependent. The most importantly, if you can tune the strength of spin, the electric field, you can also tune the strength of the spin-orbit interaction and also the effective magnetic field. So by using this quite unique feature of spin-orbit interaction, you can make this spin functionality by all electrical means. So we can call it spin-orbitronics. But in the vacuum, this spin-orbit effect is rather weak or negligible because of this denominator shown here. So actually, this is the energy gap between electron and positron. And this energy scale is something like 1 mega electron volt, which is quite huge. But in semiconductor heterostructure, this is the case for Rashba spin-orbit interaction. As you can see, this denominator is replaced by the energy gap, something like this. This is the 1 electron volt. I mean, the energy gap between electron and hole. And also, it is proportional to the electric field in the quantum well. So basically, we can tune the potential profile in the quantum well by putting the gates on top, something like this. So far, this spin, the functionality was realized by using the external magnetic field or local external magnetic field, or by using ferromagnetic electrodes. By using spin-orbit interaction, for example, by using the spatial gradient of spin-orbit interaction, we can make the Ström-Gerlach spin filter in such a mesoscopic system. And also by using the Rashba, the ring structure, we can also make, we call it Hadron-Kesher spin interferometer, which I will discuss a little bit later. And also by using this quantum point contact out of indium gallium arsenide with strong Rashba spin-orbit interaction, we can also make spin injection and detection experiments. So most importantly, this spin functionality can be realized by all electrical means. So I will not go into the detail of all these experiments, but I will discuss the focus on this Hadron-Kesher spin interferometer. As you know, this original, the spin interferometer was realized by using the neutron spin interferometer shown here. The point of this experiment is shown something like this. So by using this local magnetic fields, they actually introduced the spin precessional motion. And by controlling this local magnetic fields, they actually observed such a nice interference pattern. But most interestingly, the 2 pi spin precession does not make the original spin state. Actually, they need to have the 4 pi spin precession to make the 2 pi phase shift. Actually, this is very, very essential feature of spin 1/2 system. So this kind of the spin interferometer can be realized by using indium gallium arsenide semiconductor hexagonal structure, which has a strong Rashba spin-orbit interaction. And if you look at the electron spin traveling clockwise and counterclockwise, this is effective, the momentum-dependent effective magnetic fields. So both the electron spins start to precess in a different way. So by tuning the Rashba, the spin-orbit interaction by using this gate electric fields, actually we can control the relative, the spin orientation at this interference point. But in the actual experiments, we did use this the array of the ring structure, not single ring structure. The reason is to get rid of the additional interference effect and to pick up the time reversal symmetric interference effect. By using the gate voltage, we can modify the Rashba spin-orbit interaction, but also the carrier density of the 2-dimensional electron gas is modified. This gives rise to the additional interference. But by picking up the time reversal symmetric interference, we can cancel out this orbital part of the interference effect. So this is actual experimental data, the function of the magnetic fields. So you can see we have a so-called Alto-Schuler-Aronoff-Spivak oscillation, which has the h/2e period as a function of the magnetic field. And by increasing the magnetic field, the amplitude of the interference is going down because magnetic field destroys the time reversal symmetry. And by changing the gate voltage, you can see the amplitude of the interference is quite well modified. At the B equal to magnetic fields equal to 0, you can see it shows such oscillatory behavior as a function of the gate voltage. So this is our experimental demonstration of the spin interference. And also, if you look at the data very, very carefully, we have also h/4e. This is the 2 times round trip interference, which has the period doubling. Actually, this period of the interference is quite consistent with the gate voltage dependence of the Rashba spin-Nobit interaction. So actually, this is our experimental demonstration of Aharonov-Kasher spin interferometer. Since the spin phase is modified by the electric field, this is actually electromagnetic dual to the Aharon-Bohm effect. So actually, the original Aharon-Kasher experiment was tried to realize by using this neutron interferometer. But actually, the effect was very, very tiny, something like this. This is not electric field, this is magnetic field. But by using this semiconductor heterostructure, we do see such many oscillation by the electric field. The reason is the strength of the Rashba spin-Nobit interaction, or generally spin-Nobit effect in solid, is much, much stronger than that in the vacuum. So in our 3,5 compound semiconductor, not only Rashba spin-Nobit interaction shown here, but also we do expect additional spin-Nobit effect, so-called Dresselhaus spin-Nobit interaction. Since the 3 and 5 element has the opposite ionicity. So actually, these 2 atoms makes the dipole electric field. So this is another origin of the spin-Nobit interaction, so which has the different symmetry from the Rashba spin-Nobit interaction. So effective momentum dependent magnetic field orientation is shown by this blue arrow shown here. So if you have both Rashba and Dresselhaus spin-Nobit interaction, the momentum dependent effective magnetic fields is rather complicated, shown by the green arrow. But by using very, very narrow wire shown here, we can identify the orientation of total spin-Nobit field shown here. So by using the in-plane Zeeman field, if the Zeeman field orientation is aligned to this spin-Nobit field, then we have the maximum amplitude of the interference. So actually, this is a collaborative work with Professor Klaus Richter quite some time ago. When the this in-plane magnetic field orientation is aligned and aligned to the spin-Nobit total fields, then we do have the maximum amplitude. And from this angle dependence, the maximum amplitude position, we can identify the ratio between Rashba and the Dresselhaus spin-Nobit interaction without any fitting parameter, fitting procedures. So actually this theoretical prediction was experimentally demonstrated in this wire structure. And the point is, by tuning the in-plane magnetic field direction, we do expect such a very, very anisotropic amplitude in the oscillation or interference effect. So our question is whether we can also expect such the anisotropy in this spin interferometer. So before going into our experimental detail, so let me explain our theoretical the analysis, which was done by a group of Diego. So we do expect this Coulomb-Kircher phase, and also we have some additional phases somewhere here. One is spin geometric phase, which I will discuss a little bit later. And because of this Dresselhaus spin-orbit fields, so we do expect the anisotropy, but the situation is rather different from the wire structure. So in this case, the additional spin dynamic phase is maximum at in-plane magnetic fields around the 45° or 135°. It is well fixed, not gradually changing like a wire structure. So from this maximum and minimum value, so we can define the anisotropic amplitudes, the difference between the amplitude of 45 and 135°. So this anisotropy amplitudes again shows that the oscillatory behavior, because it can also described by using this Coulomb-Kircher phase. Actually, this is our perturbational result. So this anisotropy amplitude shows such oscillatory behavior. And this is perturbation theory, and also it's only valid for the ballistic and pure one-dimensional ring structure. So we also did the numerical calculation by using so-called quanta numerical simulator. This is actually quite powerful to simulate the mesoscale transport. So also this is quite realistic parameter to the with the experiment, and we also do see the anisotropy reversal. For example, maximum amplitude appeared at the 135 is switched to the 45°. So actually, this is quite consistent with the perturbation theory. So this is our experimental result with fixed gate voltage, namely fixed Rashba spin-orbit parameter. So actually, by rotating the in-plane Zeeman field, the experimental data, it's not so easy to see the anisotropy, but if you look at the data very, very carefully, by extracting the background signal, then you can see this red one is a little bit larger than the blue one. So it shows actually such an anisotropy as a function of the in-plane magnetic field. So we repeat these experiments with different gate voltage, namely the different Rashba spin-orbit interaction parameter. But in this case, you can see the blue one is a little bit larger than this the red one. So you can see the anisotropy is reversed from the previous one. So this is actually quite consistent with the theoretical prediction. But I should emphasize that the sign of the Rashba spin-orbit interaction is not reversed. But by changing the Rashba strength, we can see such anisotropy reversal. But we have a big mystery or a big contradiction with the theory in experiments. So this is our experimental result. So we did see, or we do see, one more additional anisotropy reversal as a function of in-plane magnetic field orientation somewhere here with relatively low Rashba parameter. But on the contrary, the theory does not show any additional anisotropy reversal. Actually, this is the big mystery for a long time. So in this, the theory, the anisotropy shows such oscillatory behavior. For example, the numerical calculation and perturbation theory. And actually, this is quite reproducible to the experiment at this first anisotropy reversal point somewhere here. But in this experiment, we do see one additional anisotropy reversal point somewhere here. So we didn't understand the origin of this additional anisotropy reversal. So we should think about this Dresser-Haus spin-orbit interaction more carefully. Actually, this is originated the bulk inversion symmetry. It has the higher order of spin-orbit effect. So we should take into account this the third order or the cubic term somewhere here. So this is actually renormalized the linear Dresser-Haus term, which is depends on the ratio between kg square over kf square. Actually, this kf square is proportional to the carrier density. So when the this ratio or kg square over kf square is little bit larger than 1/4, then the total effective magnetic field strength shows something like this. So by tuning this carrier density, if you can make it a little bit less than 1/4, then this anisotropy is switches to the 45 degree. So this is actually most probable reason for this additional anisotropy reversal. But we should be very, very careful about our experimental situation, since our heterostructure is indium-rich gallium arsenide. It's inserted in this lattice-matched indium gallium arsenide. So we should consider the penetration of the wave function into the barrier layer. So we need to solve the Poisson-Schrödinger equation self-consistently, and we should calculate this confinement effect very precisely, something like this. And also, important thing is this strain can also induce the additional strain-induced Dresser-Haus spin-orbit interaction. So actually, we can also calculate the strength of the strength, and also the coefficient can be taken from the literature shown here. So we also have to estimate the bulk Dresser-Haus spin-orbit interaction parameter. So I will not go into the detail, but by measuring over structure and wire structure in detail, we can actually obtain the bulk Dresser-Haus spin-orbit interaction parameter, something like this. And by taking into account all these parameters are experimentally obtained and theoretically calculated and taken from the literature, and renormalized linear Dresser-Haus spin-orbit interaction is expressed something like this. And this is the plot of the Dresser-Haus spin-orbit interaction. Actually, we can expect the sign reversal at this carrier density, and corresponding the Rashba parameter is somewhere here. So actually this value is quite consistent with our experimental data. Now we are quite sure that our experimentally observed one more additional anisotropy reversal is due to the sign reversal of the Dresser-Haus spin-orbit interaction. So far, many people believe that the Dresser-Haus spin-orbit interaction is material constant, but actually it's not the case. If you optimize the heterostructure, we can actually control the strength and also the sign of the Dresser-Haus spin-orbit interaction. So far, we have much focused on the spin dynamic phase, but also in the spin transport, not only spin dynamic phase, but also spin geometric phase, and also the geometry of the transport channel can really affect the spin dynamics. So actually, this is the collaborative work with Sanada-san at the NTT. So in this momentum-dependent fields, if you make this winding channel, so effective magnetic fields orientation is shown by the red arrow. So actually, this is the oscillating effective magnetic field. And this oscillating effective magnetic fields can be decomposed to the static magnetic fields and oscillating perpendicular magnetic field. So we can optimize the geometry of the winding channel, and then we can realize the spin resonance. So in this experiment, we shine the circularly polarized light, and the perpendicular spin was generated, and the spin was carried by using circus acoustic waves with the constant velocity. And the experimental result is a little bit complicated, shown here, but this experimental result is quite well reproduced by the calculation. The important thing is in this spin resonance, we can tune any orientation of the spin. So this movie was made by Sanada-san at the NTT. So in this straight channel, so it, yeah, the spin, the motion is simple precessional motion. But here in this winding channel, the motion of the spin is so complicated. Actually, this is the laboratory frame of the reference. But if you are running together with the electron spin, so the spin motion is something like this. This is actually very similar to the Rabi oscillation. So it's actually very, very important for the quantum technology to manipulate the spin orientation. Actually, this is the moving frame of the reference. So the spin, the channel geometry is rather important. And also in this, the ring structure, this curvature is rather important, which give rise to the perpendicular component of the fixture field. So because of this total magnetic fields is not completely in plane, this is a little bit tilted upward or downward depending on the propagation orientation. So during this cyclic motion of the electron spin around the ring, so actually this is from the Krauss paper. So the total effective magnetic fields can subtend this solid angle in this Bloch sphere. So this give rise to the so-called spin-orbit Berry phase. So actually this polar angle is quite important, which is determined by the ratio between spin precessional frequency and the circulation frequency, something like this, and given something like this. So the question is how to deduce, how to observe this spin geometric phase effect. The simple idea is shown something like this by the application of in-plane Zeeman field. Actually, the total magnetic field is tilted toward the in-plane magnetic field orientation. Then we can expect the modification or control of the spin geometric phase effect. To see this spin geometric phase effect, so again, we had the measurement that we did before, and this is actually a Haro-Kasher spin interference as a function of the gate voltage. So by increasing the in-plane magnetic fields, so you can see the amplitude of the interference is going down because of spin-induced dephasing effect, which I will not go into the detail. But most importantly, so you can see this oscillation peak and dip position is shifted toward the positive gate voltage region. So actually this experimental result shown here are quite well reproduced by the perturbation theory, something like this. And this phase shift is exactly expressed by the solid angle, namely, we can call it the spin geometric phase effect. Quite recently, such a Berry phase or geometric phase switching effect was experimentally discovered in so-called graphene resonator. So when without the external magnetic fields, the trajectory of the, in this case, hole is something like this. So the winding number around the Dirac point in this momentum space is 0. But by the application of the magnetic fields, they can make it the winding number around the Dirac point becomes 1. So they can expect the quite different electronic states, which was experimentally detected by the STM tunneling spectroscopy. So they can really make the such as topological transition or very switching effect in this graphene system. So the question is whether we can also see this topological transition in this spin interferometer. In principle, it's possible. For example, by the application of the in-plane magnetic fields, if the in-plane field is not strong enough, less than the spin orbit field, the total magnetic field is still rotational magnetic field. But the in-plane Zeeman field is much stronger than the spin orbit field. So this rotational field switches to the such oscillation field, and the winding number around the North Pole direction in this real space becomes 0. So we do expect such a geometric phase effect and the topological transition at this critical point somewhere here. But actual experiment is rather difficult because in-plane magnetic fields induce the induce the dephasing effect. So our idea is the following. By using this square geometry of spin interference loop. So in this case, at this corner or vertex position, we do expect very strong out-of-plane component. This assists the topological transition, something like this. So this is a spin orbit field, and this is Zeeman field. So you can see this, the state line of the interference pattern is completely changed to this checkerboard pattern. And also, interestingly, the period of the Halon-Kesher interference is 2 times longer than the original Halon-Kesher spin interference period. Again, the important thing is very, very tiny in-plane magnetic field. We do expect such a topological transition. Actually, this the calculation was already done quite long time ago by Dario and Diego quite some time ago. So basically, we follow this this calculation. And more generally, the curvature effect was calculated by Coulomb and Mario quite recently. So this perpendicular component strongly depend on the curvature of the spin transport channel. But anyway, this curvature can help the topological transition. So to confirm, okay, this is a more realistic calculation for the time reversal path because we are using the array of the interference the loops. So again, we do see such not washboard, but the checkerboard pattern, and also we calculate the winding number around the North Pole position. So this winding number change is not perfectly corresponding to this interference pattern reversal, but more or less overlap this interference pattern, for example, from here to there. So to confirm this topological transition experimentally, so we made the square loop array out of indium gallium arsenide heterostructure. And we did more or less the same experiment. By application of the gate voltage, we do see some oscillatory behavior, but the oscillation period is 2 times longer than the ring structure. We couldn't see the clear oscillatory behavior, but somehow we can see the interference reversal by the application of the in-plane Zeeman field, something like this. For example, by the application of the 1.5 Tesla this negative interference pattern is reversed to the positive interference pattern shown here. So again, this is the two-dimensional plot. By increasing the in-plane magnetic fields, so you can see that the interference pattern is completely reversed with the relatively weak in-plane Zeeman field. So this negative interference is switched to the positive interference. Actually, this is an experimental demonstration of topological transition, which is assisted by the geometry. So we can also compare it with the ring structure. By the application of the in-plane magnetic field, amplitude is going down, but we didn't see any interference reversal. We can only see this interference reversal with such a tiny magnetic field for this square root structure. And we also did the numerical calculation by the quanta, the simulator. So experimental result is more or less well reproduced by this calculation. But the situation is a little bit complicated because by increasing the diffusiveness, the interference reversal point is going down by increasing the diffusivity, and experiment is not perfectly reproduced by the theory, but qualitatively, I would like to emphasize this observed interference reversal is actually reflect the geometry assisted topological transition.
Yusaku, sorry for interrupting. You have 5 minutes left.
Okay, so this is the summary of my talk. So yeah, I will finish with this summary, and I'd like to accept the question for the audience from the audience. Yeah, thank you very much for your listening.
Okay, thank you very much, Yusaku, for your talk. So now we are open for questions. We have 5 minutes for questions. So if you please can post them in the chat.
Excuse me, how to look at the chat?
Okay,
so
I can read the questions for you.
Okay,
so don't
okay.
worry. You
Yeah,
chat.
thank
I
you.
mean, it's on the bottom of the menu,
bottom?
the screen. Yeah, at the bottom you have a window chat, and you can click there. Is there any question? If you don't have time for writing, I mean, I think you can speak loudly. You can open your microphone.
Yeah.
Maybe it's better. Please, any question? So I have a question, Yusaku. So you think there will be an independent proof of the reversal of the effective Dirichlet interaction? Could it be possible to you have in mind any other sort of experiment for an independent demonstration?
So you're asking about the reversal of the Dirichlet spin-Leavitt interaction here?
Yeah, exactly. If there's any possibility, you have in mind any other sort of experiment for trying to identify?
Yeah, I think the wire structure is easier to see this the sign reversal of the Dirichlet spin-Leavitt interaction. So maybe we need to also optimize the heterostructure, and the anisotropy of the wire structure is more flex, and we can also see this the sign reversal of by using this wire structure, we can directly relate the Rashba Dirichlet spin-Leavitt interaction. So we do expect the same reversal effect in wire structure.
I see. Okay, thank you. So any other question, please? Okay, if not, I think we can prepare Klaus, are you there?
Yes, I'm
Thank
here.
you,
Okay,
thank you, Yunsaku. Thank you very much
Yeah,
for your
thank you
for
very
your talk.
much.
Klaus, can you share your file? Yeah, okay.
Yeah, I'm
It's
just
appearing
about to
now.
share
Okay, it's appearing now.
the screen.
So the next talk will be given by Klaus Richter from Regensburg University in Germany. And the title of the talk is Magnetotransport and Quantum Hall Effect in Curved Topological Insulator Nanowires. So I think Klaus is accepting questions during the talk, right?
Sure. Yes, please.
Okay, please let me
Go
know.
ahead during the talk also. Yes.
Good.
Yeah, good morning, everybody. Good morning, everybody. And thanks to Diego and Carmine for inviting me to this mini-colloquium. If you consider mesoscopic physics or nanophysics during the last 10, 20, 30 years, the devices have been getting more and more complicated. And however, the vast majority of devices has been in 2D flat space. And the idea behind the talk today is to think of mesoscopic physics in curved space, that is on curved surfaces. And to this end, we will consider topological insulators, because there we know that they host surface states. And if you can consider now insulators that have a curved surface, then we are in business and can think of Dirac physics, say for shaped systems. Now, let me, before I come to this topic, I would first like to introduce my co-workers. That has been Rafael Kozlowski in particular. So his PhD thesis is the main part of this talk. And besides, I will talk about Coulomb blockade physics a bit later. And Ansgar Graf did his master's on that topic in my group and is now in Paris. And then two research associates in Regensburg, Dennis and Cosimo, where Cosimo contributed a lot, in particular, have also been involved. Now, if we talk about topological insulators, we know they have particular properties. And one is, of course, that they have an insulating bulk and conducting surfaces. And these surface states, which are sketched here on the right-hand side, share or have particular properties. One is, of course, the massless Dirac-like dispersion, usually, that you will have. But beside that, as sketched also here, you have spin momentum locking of the states that are at the surfaces. And associated with that, also backscattering is, at least perfect backscattering is fully forbidden. Backscattering in general is reduced if time reversal symmetry is preserved. And this, for instance, leads to the fact that you have then a metallic surface with better conductance properties as a usual metal. Now, all these properties lead to interesting applications ranging from spintronics to quantum computation, with the hope to have true technological applications, but I will refer here, of course, to the fundamental aspects. Now, if we talk about curved space, then we need to get curved surface topological insulators. And the simplest system you can think of are cylindrical topological insulator nanowires. And that's shown here on the left-hand side. They are described, can be described by rather simple surface Hamiltonians that have been established for flat 3D topological insulators. And as I will explain in a minute also, this rather simple structure still works if you have a curved space. Now, the fine circumference gives rise then to discrete values of k phi that enters here into the Hamiltonian. And this gives rise in turn to quantized angular momentum. And this quantization in angular momentum then shows up as slices here, of course, due to the quantization in the energy dispersion relation that is for the Dirac cones in these systems. So we have beside that, of course, here also kz, which describes then the momentum direction along the wire throughout my talk. And if we make also contact to the last talk by Junsaku Nita, we see we have in a way the topological insulator Hamiltonian is rather closely related to a spin orbit Hamiltonian, but the spin orbit term is the Hamiltonian already. Okay, if we go one step further, then we see, of course, now here in 1D typical band structure from these slices. Now, in order to indeed include the topological insulator properties correctly, we should go one step further or discuss this Hamiltonian a bit more in detail. So here we have again our cylindrical nanowire. I already mentioned that we get angular momentum quantization, that is the L here, the angular momentum quantum number from the rotational invariance if you go around here, around this angle phi. Now, this simple form of the Hamiltonian, however, which is appealing, arises only for curved systems if you take care in an appropriate way by the so-called spin connection. So if you start to write down a Hamiltonian for a curved surface, I mean, Carmine and Diego have done this a lot, then we find another spin connection term. However, this can be kind of scaled away or transformed away by using non-trivial volume forms of the wave functions that enter into the Hamiltonian energies at the end. And then you can indeed re-establish such a simple form where, however, now the Berry phase appears. This arises from anti-commuting boundary conditions, anti-periodic boundary conditions, sorry. Physically, of course, is related to the fact that if you have a spin transport around the circumference of your wire, then this gives rise to the Berry phase. We saw the very similar Berry phase in the last talk for the rings. Now, these systems are particularly interesting now if you have a coaxial magnetic field, because opposite to a usual mesoscopic wire where you have also bulk transport, we have now only pure surface transport. And this means that we have a well-defined cross-section and thereby, for a given magnetic field, a well-defined magnetic flux for all the states on the surface of the wire. And if we combine these different aspects, again, this 1/2 from the Berry phase opens up a gap here for zero magnetic field, zero flux in the band structure. So the Berry phase creates, in a sense, massive Dirac-like surface states. While if we switch on now the magnetic field, we see that we first lift the degeneracy of angular momentum states. Without magnetic field, we have just the left and right going angular momentum states, and this is now lifted. And moreover, and interestingly, and this has been shown by the early work by Bardason, Brouwer, and Moore, we can indeed close the gap again. That is, if we have just half integer quantum flux quanta here from the magnetic field, then you see that this just cancels this Berry phase 1/2, and then you can indeed get again massless Dirac fermions and indeed reflectionless transport for these states. Now, these are of course still, this is the simplest case of a curved surface. And we would like to go one step further. But first of all, I would like to discuss whether these theoretical estimates and thinkings can be realized in experiment. So a few words on experiment. And indeed, there are a number of different settings where people use now experimentally topological insulator-based nanowires. I mainly refer to one here, which is based on experiments by the Weiss group, just 30 meters from my office here. And these are based on a so-called strained mercury telluride, which is known to be a 3D topological insulator. And then by electron beam lithography, you can indeed etch here now thin tubes or thin wires which have surface transport. And you see the scales roughly, that is about 1 micron in length or a few microns, and the diameters of the order of 100 nanometers or so. And since backscattering is reduced in topological insulators, these systems are rather ballistic and more phase coherent. And this you can see from the right-hand side here, namely from quantum coherence effects in the conductance through such a wire. Say from the left to the right, if you apply now this coaxial magnetic field, this creates, as I explained earlier, the magnetic flux through the wire. This is this phi here. And in this experiment now, the conductance has been measured for different gate voltages. Those are the different traces here as a function of the flux. And one can easily analyze these oscillations in the flux now by taking a Fourier transform in phi. And this is shown here. However, the axes are flipped. So the horizontal axis is now the gate potential. And for given gate potential, if you go up, now that's a Fourier transform of the Arnold-Bohm type signal, you see a clear peak here. And a cut in this vertical direction is shown here on the right-hand side. There we see a clear peak now in the Fourier transform of the magnetoconductance, precisely as at one flux quantum. And this is a clear-cut signature, indeed, that Arnold-Bohm oscillations are observed experimentally in these wires. And this is thereby also test that we have indeed surface transport and no bulk transport. And then you can go on and consider further effects and the gate voltage dependence. And thereby it was possible in this paper, which is given here below, that indeed these wires host topological surface states. Now these are in a way straight wires, and one, however, can think of to go one step further, and this is shown here. So one can now think of, again, these are experimental settings from the Weiss lab, where you change now along the wire direction the diameter or the radius of the wire. So you have here this bubble, for instance, or vice versa, you can have a junction. So you have the radius is diminished here in the middle. And these systems can be very well modeled by the system given on the right-hand side. So we still stick to a cylindrical geometry of our wires, but now we see that the radius R is changing as a function of the Z, of the length scale along the wire. And this has strong consequences, as we will see later, for quantum transport. Because this varying cross-section along the wire means that we have now a tunable quantum confinement. And also, if you think of charge carriers moving along the wire, they will see a changing flux along the wire. Even the magnetic field is given because the surface changes along the wire. And more generally, from a theoretical point of view, this is now interesting because now we have Dirac-type electrons moving here on this curved space, or here in experiment in curved 2D space, where we will see in a minute what type of curvature effects then can be probed in magnetotransport. And moreover, if you go to rather strong magnetic fields, we will see that we reach a quantum Hall regime. And this arises geometrically from the fact that this longitudinal magnetic field that you see here, this will pierce the wire if the wire is banded and creates locally changing perpendicular magnetic fields. And if those are strong enough, then you will see quantum Hall states. Now, so to summarize this first part of the talk, we see we have a setting where we indeed are able to consider, well, mesoscopic or nanophysics on curved surfaces. And this is not just a theoretical idea, but we are close to experiment. But in the following, I will first now explain a bit the numerical implementation and the basic magnetoconductance mechanisms that I already envisaged. So as Junsaku mentioned, also we use the Quant software package to compute quantum transport in these wires. This is based on tight binding models of these wires in our case. So we have again our Hamiltonian here, which involves both here the vector potential, which includes the magnetic field, and here this angular momentum term. I should mention that S here is defines the is a coordinate along the wire direction, just following the surface. And since we work with a tight binding model, one has to take care of also measures to get rid of Fermi doubling. I don't want to discuss here the details, but This is done by a so-called Wilson mass term. Now we can then unfold such a wire, and then we have this just this grid, and you include antiperiodic boundary conditions to take care of the Berry phase that I mentioned. However, we have then to extend Quant and further develop it indeed to describe now a curved wire as shown here. Because now we have, instead of Z, we have now this parameter S that parameterizes just the length here along the surface. And we include now the shape of these tubes in this unrolled scheme by a locally varying hopping or lattice constant. And this enters through this 1 over A of S, where A of S is just this lattice constant that depends now on S, because depends on the diameter or surface or circumference of the wire. And thereby, however, you can include indeed also then in the piles phase such non-uniform lattice effects. But this more technical remark, let's go on and consider what does it mean if we have a wire where indeed the radius changes with S or along the wire direction. And well, briefly again, we start from this Hamiltonian I showed earlier. We then use a separation ansatz to get rid of the angular momentum part. You see here the angular momentum quantum numbers appear again. And this gives rise then to, for a given L, if angular momentum is a good quantum number for these rotationally invariant systems, then you get individual Dirac equations for the different L's. And beside the kinetic part along the wire direction, you have now this additional mass potential. We call it a mass potential because it's not just a scalar potential, but because it comes with here with the sigma y Pauli matrix, which is off diagonal. Now, what enters into the mass potential? This is on the one hand a kind of a centrifugal term, and this is also governed by the wire geometry, 1 over R of S, so it depends locally now on the radius. Then we have the angular momentum quantum number we had earlier, we have the Berry phase, and now we have a flux which depends also on S, on the position of the wire. And altogether, this gives rise then to an effective potential for charge carriers moving through the wire, given by just the absolute value of this mass potential. And this is shown here now on the right-hand side. So if we take a rather simple system, just a wire with this kind of constriction with 2 different radii here, then the different radii give rise to, for given fixed magnetic field, now to different fluxes along this wire length S. And the different flux enters here, of course, and the different radius into this potentials. And then you see that already such a small constriction, rather simple geometry, changes now the effective potential strongly, depending now on the magnetic field and wire geometry. And in particular, we see here for given, now this is now given for different angular momentum. If we take one angular momentum, we see that you can get now kind of a magnetic barrier for the electrons which would like to move from the left to the right. And this has, of course, a direct consequence for transport. That's shown on the next slide. So we, again, on the right-hand side, we have the effective potential along the wire for given angular momentum channels. And if we go up in energy now, we see that there's a big gap up to 6 milli-electron volt. That is this range here, where we don't have any open channel. We have this blocking due to this repulsive potential barriers. However, if you go up here above the first barrier, then we get indeed steps in the conductance that are just associated with the barriers we see here in this effective potential, and so on and so forth. So interestingly, to summarize this, we have the change of the wire geometry. It gives rise to a change of flux. In both quantum confinement and flux creates an effective mass potential. And I already highlighted that we have a mass potential. This is important because it's not electrostatic. Electrostatic potential would be subject to Klein tunneling. So charge carriers could just tunnel through such a potential well, but here it is of magnetic mass type origin, and thereby it acts indeed also for Dirac particles as a true potential in the way we know it from Schrödinger particles. And this gives rise now, and you see there, by changing the wire geometry, you can artificially devise potential landscapes. Now, I would consider this in particular now for a particularly interesting case, and this is the case for strong magnetic fields. There we can even stick to very simple structures, and this is this nano cone that I show here on the upper right part of the transparency. So we don't have a constriction, we have just now a cone with increasing radius that is matched in between two cylindrical wires that are not shown here. In transport, we would measure now from a cylindrical wire, we enter the cone and leave the cone again. And a typical conductance profile is shown here on the left-hand side. The conductance, again, as a Fermi energy at 2 Tesla here, with a bit of disorder, which also we, to be closer to experiment. And we see then that for these intermediate magnetic fields, we have a conductance trace, which is completely different to the one we saw earlier. Here we had clear steps in the conductance, and now we see these resonant type peaks here. And the question is, of course, now how do they arise? And since the magnetic field is strong enough such that the associated magnetic length is shorter than the geometrical parameter of this cone, we can check whether this has to do with the quantum Hall effect. And indeed, the peak positions here are precisely coincide with the energy levels that you get in the following way. You see here in the upper right part, the magnetic field, of course, pierces here also the surface and creates a local perpendicular magnetic field, B perpendicular, and this creates quantum Hall states. And if you use now for Dirac systems, the formula that is a square root of the magnetic field times the quantum Hall occupation quantum number, then indeed you get quantum Hall levels that indeed coincide with the resonances we see here in transport. Now you may ask, how is this compatible with the picture of this effective magnetic potential that I have been putting forward before? So we have now 2 different views. One is just the quantum Hall levels, and the other these effective magnetic potentials. Now, well, we can indeed make this compatible. So we can compute now also for this nanocone here, these effective potentials. And this is just S is here, describes the length of the nanocone from 600 to 1,200 nanometers, starting with the point where the nanocone would close. So this is right, precisely this length scale here. And you see then that you get a number of now effective potentials that are nearly linear, and this has to do with a strong magnetic field. So each of these wedge type potentials corresponds to one angular momentum quantum number again, as discussed earlier. And we have 2 exemplary cases here with 15 and 25. Now you can quantize and solve the Schrödinger equation in each of these wedges, and you find degenerate eigenstates which you perfectly coincide with the quantum Hall level. So we see here that this effective potential picture is just another way to describe the quantum Hall system. Now, if you would have a system that is perfect without disorder, then the different angular momentum states in the different wedges would be have no true overlap because they have different symmetry. And that would mean that if you have now transport through the system, that is, you enter from the left here, you should tunnel into such wedge, into a quantum Hall state, then you would, the tunneling to the right-hand side, which is far away, would be exponentially suppressed. So in a purely clean system without any disorder, you wouldn't see any transport. However, with disorder, we see here indeed, then the quantum Hall states between different wedges couple, and you have a kind of a disorder-mediated transport. And you can now consider different type of disorder strength. So if we have weaker disorder, this is these green curves, you have a smaller peaks. So we see here that if we increase this order in the system, we increase in a non-trivial way indeed the conductance through the quantum Hall levels. Okay, now you might ask what happens if I take this very same geometry, but now change the magnetic field direction. Now I have magnetic field that is perpendicular to the axis of the nanocone. And for this nearly same situation, the conductance changes completely. You see the quantum Hall states disappear. You have just now again a conductance which is increasing with a, however, prominent plateau, just one flux quantum here in a broad energy range. So how to understand this physics here? It's still quantum Hall physics, but from a different point of view. Now the magnetic field creates, which is now pointing upwards, has a rather strong perpendicular component in the upper and lower part of the cone, and here quantum Hall states reside. While at the left and right hand side here, or rear and front part, you have regions where, as a function of phi, the angle here, you have just a zero perpendicular field. And these fields give rise to so-called chiral hinge states. Those are states that propagate mainly reflectionless along the topological insulator here. And this idea or picture can be put in a more general framework, and this is the framework of what one calls these days extrinsic second-order topological insulators. So the idea is here to have a 3D topological insulators like this cube here. It is called extrinsic because you put this in an external strong magnetic field. And then you see that in the upper part and here at the sides, you have quantum Hall phases, but from a classical point of view, creating cyclotron orbits with different sense of rotation here, because here the magnetic field enters into the cube and here it leaves the cube again. And at the interfaces again between these quantum Hall phases, you have what is called then the 1D chiral edge mode, which follows here these edges of the cube in this general case. And that's why these topological insulators in this case are called second order, because you have a three-dimensional TI that hosts one-dimensional edge states now. And in our case, the physics is rather similar. It's shown here. In the middle part, we have now computed, again, as a function of S along the tube, along the cone. And phi is just here, now the angular degree of freedom again, the current density along the system. And you see then that in the regime where you have this plateau, you have just one edge channel, one chiral hinge state moving along. And this cannot be backscattered because the back-moving state is far away in space. Very similar to the quantum Hall effect. And thereby you get this nicely quantized plateau here, even for these nanostructures. Okay, to summarize this main part here, we see that if we consider a perpendicular magnetic field, you can indeed consider many different types of building blocks of these nanowires. The physics here is rather solid and rigid. You mainly see indeed for the perpendicular magnetic field and then these chiral side surface states, which provide also spin transport just without back reflection. And thinking of possible experiments, we see again, if we compare the two cases, if we have the case of a collinear magnetic field, we saw these Landau levels. And in an experiment, you could in principle just rotate now your magnetic field, use the same sample, and then you would expect, and we expect a completely different transport characteristics now. So to take home message of this major part of the talk is that if we consider this, indeed now these wires with changing radius in magnetic fields, if you have longitudinal magnetic fields, then you create effective potentials, you can devise potentials and thereby strongly, well, you get transport that strongly depends on the geometry, you get quantum Hall signatures as I showed, while if you have these strong perpendicular magnetic fields, we get these rather robust chiral side surface states. Now I see I have just, I think, a few minutes, 2-3 minutes left. And I can just show 1-2 further transparencies to show another example where now these effective magnetic potentials that I have been introducing may play an important role. And that is Coulomb blockade physics. But to go to that, I will just come back to this transparency I showed earlier, where we saw that just a change in the radius creates here strong magnetic potential wells. Now you can think of combining different of these building blocks, for instance, 2 of them, and thereby the 2 constrictions will create 2 magnetic potential wells. And this allows you now to create magnetic quantum dots. So we talk about a quantum magnetic bottle. You might remember a classical magnetic bottle is what we learn in experimental physics. That is a classical charged particle in an inhomogeneous magnetic field where the inhomogeneity then allows to capture a classical particle. Now here, our mechanism to confine particles is purely quantum via the Antwerp-Bohm phase. And then if you think of such a geometry, you can think of now hosting indeed states in such a magnetic quantum dot. Now I will give one example and come back to the nanocone because this simple geometry is already enough to show quantum Hall physics. So we have again here our nanocone now in between our 2 wires and measure transport again. So far I didn't discuss any interaction effects, and I will do this now on a kind of a mean field level. But let's come back first to our effective picture. Earlier on I showed that we understand the quantum Hall physics in the system if you have the magnetic field coaxial in terms of these number of wedges related to the angular momentum states of the system. And this is again here now the effective potential as a function of the system length here, Z. And you see that you would have degenerate quantum Hall states. With a bit of disorder, this will slightly lift the generalities. Now it's important that they arose from the perpendicular field component of this magnetic field. And at the 2 junctions where you fit now the cone to the cylinders, you have a regime where the perpendicular magnetic field locally is weaker. And this gives rise then to local energy shift that the corresponding quantum Hall states on the left-hand side here and on the right-hand side of the cone are reduced in energy. This in turn means that you get effective magnetic barriers. So think of electrons entering here, say at 30 milli-electron volt. They need first to tunnel through this magnetic barrier before they reach the inner part of this magnetic quantum dot and before they can tunnel out again. And thereby you can create again essentially now a magnetic quantum dot and think of Coulomb blockade physics. And this is now particularly interesting because now different Dirac features happen. So in a very simple picture now, I assume just a charging energy. The overall physics is much more complicated. You have to include now disorder, you have to include the correct, well, you compute the correct tunneling depending on the geometry of your system and of course interaction effects. But to get a first idea of what happens, you can just use a constant charging energy model based on the system I explained here. Now, interestingly, if you start with the lowest Landau level and think of now, how does it change with magnetic field? This is shown on the right-hand side. It doesn't change. Moreover, there is no magnetic barrier on the left and right-hand side. So you will have always, even if you're in the Coulomb blockade regime for the higher Landau levels, here resonant transfer through the lowest Landau level. That would be a peak here at a given magnetic field. And now, if you think of the first Landau level, this will roughly increase linearly with magnetic field. And now you can add a charging energy. We assume just 1 milli-electron volt, and this gives rise then here, or would give rise to a Coulomb blockade peaks here with a certain spacing. A sequence of Coulomb blockade peaks, if you go up in energy now, much higher, up to the case where you fill all the degenerate Landau levels, the first Landau level, with electrons, and then you will need to get to the next order Landau level and will have a peculiar shift here again. So at the end, you see that you will get a conductance spectrum in the Coulomb blockade regime that reflects the Dirac spectrum on the one hand, and moreover, it is in a way all magnetic. So we don't need electrostatic barriers to confine particles. We have just magnetic barriers, and we can even, instead of having a gate voltage, you can also tune the levels just by changing the magnetic field here, which is coaxial. Okay, I should come to the end. I think as an outlook, I would just mention that maybe what could one do beside what I have shown? We can think of quantum Hall physics more generally in curved space. We can, what we do already is consider hybrids of these small building blocks, now also with superconductors. And maybe even more interesting, these 2D Dirac physics in curved space that we have here in condensed matter is rather closely related to quantum gravity models. So people talk about also the same systems as model systems for completely different reasons. So we have charged particles on surfaces with constant negative curvature, as shown here on the right-hand side, which in principle we can mimic now also in experiment in condensed matter. Okay, with this, I would like to thank you for your attention and hope for questions. Thanks a lot.
Thank you very much, Klaus, for your very interesting talk. So we are now open for questions. We have 5 minutes for that. Any questions?
Can I make a question, Diego?
Yes, please, Dario.
Yeah.
Klaus, nice talk. One question: when you have the nanocone and you introduce the perpendicular magnetic field to the axis of the cone, you try to explain the perfect conductance by looking at the analogy with the Hinge states of OT. But in the end, for the electrons on the surface, this is nothing else than a snake state. I mean, you have two counter-propagating snake state, isn't it?
Yes. So for this case, you can also, you can interpret this as a snake state. It is related, of course, also to because you have just at the both boundaries of the states, you have just the opposite magnetic momenta. The important thing is that these states are, and this has to do with the band structure of the topological insulator. Then that you don't have a easy mechanism for backscattering. Only if you go to another energy regime. Maybe I can just go back to this transparency. I think it's here. So you see here, we have, if we are low enough in energy, then we have induced quantized conductance because we have just one quantized state going here from left to right.
Yes.
If we go higher in energy, we will have more states. The next, we would have 3 states on each side. However, they can now, because you have 3 states on each side, they can backscatter. And that is why the conductance is still increasing, but no longer quantized.
Okay, thanks.
Good. Any other question?
Diego?
Yeah, who's that?
It's Carmine.
Carmine, yes.
I would have a question. Klaus, you mentioned that when you do this simulation in quanta, you use these additional terms to get rid of the fermion doubling theorem, right? We have only one Dirac cone. So my question is, if I would not consider those terms, so if I would do something for a regular system with the 2 Dirac cones, would I have a response in transport that would be qualitatively different from what you have with a single Dirac cone? So my question is, if you have some transport response that really pinpoints the Z2 invariant of the strong free DTI.
Let me go back to the. Now let's take this Hamiltonian again, but
yeah.
So mainly, I mean, what you get is you get if this fermion double, you refer to the fermion doubling term, I guess.
Yeah.
Yeah. So usually you would get then, because that's a kind of an artifact of the Stein binding models, as you know, then we get spurious, also at a given energy, further spurious states. And they, of course, will change the conductance. And they, I mean, you get non-physical additional contributions. And one has to, so they are non-physical, indeed. So, and then there are different ways how to get rid of these terms. And one is related to what I mentioned, what is called a Wilson mass term. This helps then to lift them away. They are shifted away. I don't have the figure now or a band structure, such that only the true physical states play a role indeed.
Yeah. So just for me to understand, so if I would like to make I don't know, some simulation for some normal insulating materials that has two or an even number of Dirac codes, like normal time states, then you would get contributions, artificial additional contribution to the conductance in your setting. Yeah, with respect to 3DTI.
Yeah, if you have more Dirac points, of course, then, I mean, if they are there physically, it would be, no, they would be included. Yeah, one has to be careful there. One has to check then, depending on the system and the parameters, indeed, what type of measure, I mean, what type of term you include. Also, the Wilson mass term is, of course, then an artificial term, and one has to be careful that this term, again, does not kind of mask the true physics.
Yes, sir.
Yeah, it's a bit an art. I mean, Raphael, the PhD student, it took him quite some time, let's say months, to do this correctly, because there's not so much literature really on how to precisely deal with these aspects.
All right. Okay. Yeah, thanks a lot.
Okay, thank you very much. Okay, time is over. Klaus, you have an additional question on the chat. Maybe you can ask. Maybe you can answer that privately.
Yeah, of course, I will have a look to it. Yes. Yeah.
Okay. So, okay, let's go on. The next talk will be presented by Paola Gentile from the University of Salerno. Paola, are you there?
Yes, I'm here.
Okay,
so
I think you can
you
upload.
hear me?
Yeah, perfectly.
Okay.
So you can upload your talk. So your presentation. Yes. So Paola's talk title is Geometrically Driven Effects in Curved Superconducting Nanostructures. So Paola, if you can.
Okay, I'm ready. Okay.
Good, perfectly.
Can you see?
Yeah.
Okay, fantastic. Okay, sorry, I would like to remove this bump. Okay. So thank you, Diego, and thank you to you and Carmine for allowing me to give this contribution to this mini-colloquia. And as you already announced, I'm going to describe the effect of geometry on superconducting materials at nanoscale. So I come from Salerno, from CNR Spin, and this work has been done, comes from a collaboration between my group with Mario Cuoco, our postdoc, previous postdoc Jean and Gianluca, with the group led by Carmine before in Rese and now in Utrecht. And it started during this CNTQC project, which was financed by the SEND framework program, and which actually was addressing curved nanomembranes for topological quantum computation. I will describe part of the results we got during this project and also some new results we got afterwards. So the main motivation which was at the basis of our investigation comes especially from the experimental advances, recent experimental advances showing the possibility to develop ingenious design strategy to develop three-dimensional structure out of 2D conventional films, the so-called nanomembranes. And so these are just few examples of what has been done so far from the experimental point of view. For instance, the rolled up nanotechnology, which is based on selective etching, and essentially it exploits the gradient, the gradient orthogonal to the films to allow this rolling procedure, and it has been successfully applied for creating tubes and rings, for instance, of magnetic materials, semiconducting, and so on. More or less with the same strategy of strain, based on strain, many other achievement have been published in literature. So we can see these very nice figures. What is important is now, what matters here is the scale. So the scale is down to micrometer and even 10th of nanometers. And this is very important because actually this nanoscale is very challenging to reach from a fabrication point of view. Another possibility, which is completely different, has been considered by our partner in the project with this focused ion beam etching procedure. So starting with a flat film, by using focused ion beam etching, Ivan Veramanun and Dennis Makarov were able to create this template showing a finite curvature down to 47 nanometers for the radius of curvature. And then this has been exploited to demonstrate the role of curvature also in spintronic devices. Now, what I'm going to discuss here is, first of all, the effect of curvature on quantum mechanics of materials which do not have superconductivity. This is, let's say, the ground from which then I will build up a discussion for superconducting materials. So, as it is possible to see here, by combining the conventional, so if we start with low-dimensional system characterized by an atomic spin orbit coupling, so semiconducting material, let's say, and we consider generic shapes for these systems, it is possible to derive, starting from the usual Dirac-Schrödinger equation for materials having atomic spin orbit and including the confinement and the curvature of this generic shape. So a T-wall quantization procedure, we can end up with an effective 1D Hamiltonian, which is of a K dot P type, which is parameterized by this curvilinear coordinate, which actually describes the way in which particles move along the generic profile. And more interesting, this Hamiltonian contains a term which is a Rashba-like term, depending both on the atomic spin orbit coupling and on the local curvature. Of course, since the shape is generic, the curvature can change point by point, and actually this Rashba-like term depends both on the amplitude and on the direction, on the local projection of the spin along the normal and the tangential direction, which are defined in this way and are related to each other exactly through the curvature. So this Hamiltonian actually is very relevant for the quantum mechanical behavior of this system. And I just catch what happens, the main striking effect is derived for the average spin of the system. So in the normal state of this system, this semiconducting system, it's possible to characterize the effect of curvature and spin orbit coupling in terms of this effective field, as already Professor Nita showed. So actually, the curvature, a finite curvature in a generic nano-shaped system, actually play together with the spin orbit coupling to give rise to a sort of spin torque field, which allows the spin to settle inside the system with a specific pattern, which can be driven by geometry. As it is possible to see in this sketch, we calculated the average spin, starting with the case of a ring and then squeezing in elliptical form in such a way to allow the curvature to become from homogeneous to inhomogeneous. So the region of maximum squeezing corresponds to the region of maximum curvature. And as it is possible to see here, by increasing the squeezing of this ring, the spin, which is represented by these arrows along the profile of the system, actually develop a texture which is no longer trivial. In particular, the homogeneous curvature gives rise to a component which is out of plane for the spin, and then the homogeneity of the curvature coming from the squeezing is also able to give rise to tangential components which allow the spin to wind along the normal and the binormal direction. So this is supposed to have a profound implication when one introduces the superconducting pairing. The other ingredient that we have to take into consideration is the fact that the Rashba spin orbit, together with superconductivity, is supposed to have an important effect. In particular, since Rashba spin orbit coupling is a source of inversion symmetry breaking, when combined with the spin singlet superconductivity, it is expected to give rise to a mixed parity state, which also includes spin triplet superconducting correlations. These correlations are usually described in terms of a vector due to their vectorial nature, the spin triplet state. They are described in terms of this D vector, whose components actually comes from the different spin states in the triplet channels. What is actually important is that this D vector usually points along the direction which corresponds to the vanishing direction of the total spin. Said in a different way, from a quantum mechanical point of view, it's possible to demonstrate that this direction actually corresponds to a direction perpendicular to the plane where equal spin component of the spin triplet states are aligned. So we know it has already been established that for flat system, when a spin triplet correlations develop inside the system because of the spin orbit coupling, they usually are parallel to the spin in the normal state. This is valid both for the 1D direction, for the 1D states, but also for the two-dimensional systems, where because of the Rashba spin orbit coupling, the spins in the normal state develops a specific, a non-uniform pattern along the Fermi surface, as it is possible to see here. Also, in this case, the D vector keeps the direction which is parallel to the spin in the normal state. So the question is, does this picture hold also in the case of a shape-deformed nanostructure where the spin comes to have a very peculiar pattern because of it has a specific texture driven by the curvature, and in particular by homogeneous curvature? So the main question that we addressed in this investigation deals with the effect of geometry and nanoscale deformation on, first of all, the amplitude of the superconducting order parameter, the orientation of the vector, and then on the topological character of the superconducting state. So in order to address this problem, we actually exploit the Hamiltonian we have derived for semiconducting system and mapped it on a discrete lattice, considering then the presence of a non-site superconducting pairing, so developing on the same site between spin of opposite electron with opposite spin, and also non-local pairing, which actually established between opposite spin electrons sitting on different sites, on nearest neighbor site. Here, the information about the shape of the structure is fully contained in this spin-dependent hopping, which is actually the Rashba spin orbit, and it's codified inside, is encoded in this in the amplitude of the spin of the spin matrix, which on turn depends on this polar angle, which defines locally the tangential and normal direction, and so encodes the shape of the system. So the analysis has been performed by comparing, in particular, three different cases, so a straight wire, a ring, and a deformed elliptical ring. So as it is possible to see in these two contour plots, where we report the average superconducting order parameter, we found a sort of universal behavior in the sense that the average superconducting order parameter has exactly the same behavior in the straight wire ring and elliptical ring, does not actually depend on the specific form of the system, or the specific shape of the system. And in particular, we found that by defining G, the pairing, the superconducting pairing interaction, and considering only the on-site pairing, for this analysis, we notice that the spin orbit, the Rajba spin orbit coupling is always detrimental to the superconducting order parameter. So there is a threshold above which superconductivity is destroyed, and this threshold strongly depends on the pairing. Larger is the pairing, larger is the spin orbit coupling that is necessary to destroy is necessary for destroying superconductivity. On the other side, the effect of the filling of the chemical potential is represented here, and so we notice that the region which is which is more favorable for superconductivity is around the value of the chemical potential at the band edge, and this actually can be understood in terms of the density of states of this system, which is 1D, and so it has a band of singularity around exactly the at the band edge. Then increasing the spin orbit, we notice that the region where the superconductivity can exist increases, and this actually comes from the fact that the bandwidth is enlarged by spin orbit because of this K momentum splitting, let's say K momentum splitting, okay. Now, this is what happens for the average order parameter, which shows that the shape is not important, but the shape of the system becomes important when we look at the space evolution of the superconducting order parameter. As it is possible to see here, the superconducting order parameter can be tuned by squeezing the shape of the ring, and in particular, more we squeeze, more we allow the order parameters to have a local variation with a maximum amplitude around the point where the curvature is maximum. The same role is played by spin orbit coupling, which also allows the system to develop an increasement around the region where the curvature is maximum. So there is an interplay between these two ingredients. And then finally, the chemical potential can have a double role in the sense that it can both enlarge the let's say it can both increase the local superconducting order parameter at especially at half filling, but then because a mass renormalization effect, there is can happen a strong suppression at the band edge. So actually, we demonstrate that it's possible to tune by geometry the local order parameter in such a way to have region with larger and the region with smaller order parameter with homogeneous order parameter in such a way that spontaneous weak links can be created inside the system with a profound implication in transport. For instance, they can allow intrinsic Josephson junction effect.
Paula, sorry for the interruption. Yes. We have 5 minutes.
Okay, okay. About the director, we noticed that the director has a non-trivial texture as expected because of the texture of the spin in the normal state. But as it is possible to notice here, where the green line represents the evolution of the spin along the real space direction, and the blue one is the director, there are profound differences between the orientation of these two, and they are actually driven by by geometry. Indeed, more we squeeze or more we increase the spin orbit coupling, more they differ. And so we can conclude that in curved nanostructure, the vector is no longer parallel to the spin as observed in the flat systems. Okay, these are just two possible examples we can discuss in the question if needed, where we can realize this kind of system. I just jumped to the topological superconducting state. So about the conventional superconducting pairing, we know that by adding Rajba spin orbit coupling, in order to get superconducting topological state, we need magnetic field, which leads the system to go into the D class with Majorana edge states hosted at actually at the edge of 1D wire. A completely different situation can happen if we consider no local pairing. In this case, it's possible to allow a topological state even without magnetic field. The system is in D3 class, and it is characterized by the presence of a time of a Kramer spares of Majorana states. These Kramer states. So the question is it possible to tune the topological state by geometry? And we analyze the system starting with the symmetry, the symmetric ring geometry, showing that it's possible to actually map the Hamiltonian of the a perfect symmetric ring to the case of the straight wire, so that in the thermodynamical limit, they are completely equal. And this demonstrates that the case of the ring is completely equivalent from the topological point of view to the straight wire. A completely different situation can be found if we squeeze the system. And indeed, the squeezing can have can drive the system from a topological to a non-topological state at finite sites. So n is the total dimension, total number of sites of the system. And but playing with the squeezing, so deforming the system or reducing the spin orbit coupling, is possible to modify the topological character of the system. Now, what about the topological state of this system when squeezing? So the squeezing of, for instance, a semi-elliptical system having which is in the topological regime, can allow the system to develop, besides the Kramer spurs or Majorana states at the end, additional in-gap states, which develops more inside the gap, more we squeeze, and which can have, profound effect on the Josephson effect. I will just discuss this picture. We compare the Josephson effect between two semi-elliptical squeezed system where there are these in-gap states at the center of the ellipse, with the case of a Josephson junction realized with a straight wire in the topological regime with the Kramer's states at the end, interface to a system with this deformation of elliptical shape. And so we notice that it's possible to have a huge amplification of the Josephson current. Notice the numbers. In both cases, but of course, looking at the quantitative difference between the scale, we notice that the interaction among these in-gap states allows to have a Josephson junction much more increased than the case when these states are interfaced to the Kramer's states. Actually, this shows that the topological nature of this material can be fruitfully manipulated by geometry. So since I think I am out of time, I will just sketch the conclusion, and I hope I open the session for questions. Thanks a lot.
Thank you very much, Paola, for your talk. So is maybe we have time for a really brief question, if any. Questions, please?
Hi.
Yes, who's that?
It's me, Adrian.
Please.
Okay, thank you very much for your nice talk. I would like to address just one question. Is it some technological limit to the size of the system you can perform in which you can try to observe these behaviors?
Okay, so the main ingredient is, of course, the possibility to exploit geometry in such a way to, let's say, to see the quantum effects. And quantum effects coming from geometry, and especially from curvature, usually comes out when you go down with the sides of the system in such a way to achieve curvature radius of the order of 10 nanometers. So this is actually the limitation. Larger is the system, let's say, lower is the probability you can catch these effects.
Okay, thank you so much.
You're welcome.
Yes, thank you for the question. So Paola, thank you very much for your talk. So
thank you for this opportunity.
Let's go on with the program. So the next speaker is Hernan Santos. Are you there, Hernan?
Yes, I am here.
Yeah, please upload your presentation if you are able.
Sure.
So Hernan Santos is the next speaker. He's from Universidad Rey Juan Carlos from Madrid, and his talk title is Spin Polarized Current in Corrugated Graphene Nanoribbons. So please, Hernan.
Thank you very much, and thanks to the organizer to give me the opportunity to present this work. I am going to present in this talk how a spin polarized current in corrugated can be given in corrugated graphene nanoribbons. This is a work in collaboration with researchers from Spain and Brazil. And in the picture, schematic picture, you can view how a non-spin polarized current through the corrugated graphene nanoribbons can transform into a spin polarized current. I will see the details of these systems. Okay, everybody has known that graphene, the extraordinary properties and novel properties of graphene, but it's in the field of electronic at the nanoscale where this material enhance these properties. Then this material has been proposed in many parts in electronic device, as for example in integrated circuit. Okay, but it's in the field of spin and value degree of freedom where the researchers are take advantage at this moment. Okay, then in spintronic, that is the art of manipulating spin using spin orbit coupling. It is necessary the spin injection, spin manipulation, and spin detection. In that way, several works have been proposed how to manipulate the spins in graphene nanoribbons. In this group, by means of other material on the graphene, can be controlled these issues of the spin. Okay, but it's in the geometric things of graphene where graphene can be enhanced the properties. In that way, Winkles had been proposed to be to control this thermal engineering. Okay, then in the second work, by means of strain engineering, excuse me, I can. By means of strain engineering, they can control the separation of the Winkles of the corrugation and the control the curve of the corrugation. In other words, in 2D crystal, have been proposed the same. By means of strain engineering, they can obtain corrugation in several materials. Okay, but what is the physics under the corrugation? Corrugations can get an asymmetry of the p-set orbitals. This generates that a difference between the density in the inner part of the corrugation than in the outside of the corrugation. This induces an electric field from the less density to the total density in this case, and this produces a Raspberry spin orbit interaction. In that way, the proposed device by several corrugation has been made with alternating electric field, positive and negative. Thus, this generates an alternating local Raspberry spin orbit coupling. Okay, that is proposed in the down image. Okay, it's important that between the Raspberry areas there will be no Raspberry area because there are not a curvature of graphene nanoribbons in this case. Okay, in other way to create this kind of device is deposit over contact several gates. These gates produce an electric field.
Sorry for the interruption. I don't see your presentation. I see only one single slide. I don't know if you're passing them or not. If there's any problem. They are not passing. For some reason, I see only the first one.
Excuse me.
Yeah. Now I see another one. Yeah. So please go on. But at the beginning, there was only one single slide that was not passing.
Ah, okay. Sorry. Okay. Then another for to another shape to do this system is by means of deposit the graphene nanoribbon over several contacts. This contact can create electric field as the electric field produced by the corrugations. Okay, in that way, multiple gates in planar graphene nanoribbon can be similar behavior of the corrugated graphene nanoribbon. Okay. You can see I passed the presentation.
No, it's not passing. You are on page 6. You were on page 6, now page 7. Okay, just use it like this if you want. But they were not passing.
Okay. Then I summarize the proposed device, the proposed system. In the left column, you can see the corrugations, and in the right column, you can see the multiple gates that correspond to the corrugation, have the same behavior. And in the center, the model system. Okay, one corrugation can be modeled but homogeneous area in the center between the contacts. This is the behavior can be done but one gate. Okay, that generates an electric field and produce and Rasbach spin orbit interaction. Okay, bubbles and separated winkles can create two areas with positive Rasbach interaction in the center. Two corrugations can generate positive and negative Rasbach areas, and in that sense, even number of corrugation can create and truncated superlattice, positive, negative, positive, and so on. Okay. This is the model.
You are in page 7. You want to go to the next one?
This is, I am in 8 now. Sorry.
We've lost your presentation. You have to upload it again, I think. Okay.
Okay. Sorry. To model this system, we employ a one orbital tie-bonding Hamiltonian with a kinetic pair and Rasbach pair. Okay. And to calculate the electronic properties of the heterogeneous material like this, we employ a surface green function matching method. And so to obtain the transport properties of this kind of system, we use the Coulomb and Antwerp formulas, okay, where the auto energies joins the contacts and the central pair. Okay, I passed to the results in slide 9. Okay. Yes, now I propose first this system. This is an unchaired graphene nanoribbon with a site 11. Okay, there are two configurations where in the center there are a pair of the Rasbach positive and Rasbach negative in blue-green, and the two pairs positive, the other configuration. I would like to show the conductance spin resolve conductance, and in dotted line it is presented the pristine nanotube resolved by spin. Okay, then the result for the conductance up it's not noteworthy that this is the spin direction in the wave direction. Okay, this is for down. Now the first difference is that in the system with positive, the two pair positive, there is a difference between the conserved conductance. Okay, spin conserved conductance. But in the other system, in the positive and negative system, there is a difference between the spin flip conductance. This gives different polarizations that is plotted in this figure. Okay, in the system positive and positive, the polarization is negative, and in the system positive and negative, the polarization split to positive, and the polarization is coming from different conductance. Okay, one from a conservant conductance and the other from spin flip conductance. The other spin direction has null polarization. Okay, other system like zigzag graphene nanoribbon show similar behavior. Okay, it has a null polarization for the X and Z direction, and Y direction has a polarization. But in other way, zigzag graphene nanoribbon, anti-zigzag graphene nanoribbon with site 11, the polarization in the other direction are different from 0. Okay, this is the main difference with the other zigzag graphene nanoribbon. And the anti-unchained graphene nanoribbon happens the same. Okay, but why the polarization depends on the ribbon shape? This is because the symmetry. The response is the symmetry of the ribbons. That when we operate with symmetry, real symmetry to the Hamiltonian, Rashba Hamiltonian, we need to the spin space symmetries. Okay, this is the novelty of this work. I will put an example. For example, zigzag graphene nanoribbon that has a mirror symmetry in the Y direction. Okay, when we operate with this mirror symmetry to the Rashba Hamiltonian, the Hamiltonian changes the sign in the last part. Okay, then we need to restore this Hamiltonian a rotation in the Y direction of the spin, real spin space symmetry. Okay, then total symmetries leads invariant the Rashba Hamiltonian. Okay, this can be viewed in the conductor relations. When we change when we apply the spin symmetry, we are done that the spin direction change the sign in the X and Z direction. Okay, while the Y direction is the same. Okay, in that way, for spin X and Z, the conductance relation are the same and there are not spin polarization. But when the spin is in the Y direction, there is a spin flip polarization and a spin conserved polarization. Here I summarize all the symmetries, real symmetries of the ribbons employed and the corresponding spin space symmetries for each space symmetries. Okay, for real space symmetries, and its corresponding conductance relation that gives polarization or not polarization. In blue, there is no polarization. In red, there is polarization obtained from or conserver or spin flip polarization, or spin flip conductance. And when the square is red, there is a polarization, full polarization, obtained from spin flip or spin conserved conductance. Sorry. This is for the other system, for the other configuration, when there are all positive or an odd number of corrugation in the system, the conductance relation changes, and of course the polarization. Okay. In this slide, I am showing you how to enhance the spin polarization in these RASBA systems. Okay, we increase the length of the RASBA area. We observe that the polarization is increasing, and also when the non-RASBA area between the RASBA area is increases, the polarization also enhanced. Okay, here in the left and the right panel, you can see how the integrated polarization obtained for the case positive cases has enhanced for when the number of areas increases and when the non-RASBA area also increases. Okay. Then, for conclusion, spin polarized carbon can be created in graphene, corrugated graphene and ribbon. We relate the appearance of the spin polarized carbon to novel symmetry relations between the spin-dependent conductance. Also, spin polarized carbon in superlattice can be enhanced with respect to the continuous case. Finally, the studied symmetries can be applied to other 2D crystals to find possible candidates to form a spintronic device. Thank you for your attention.
Thank you very much, Hernan, for your talk. We may have time for one brief question, please. So,
can I ask something, Diego?
Yes, Dario, please.
In the plot where you show the conductance versus a parameter that is the energy, is this parameter that changes the spin-orbit interaction?
In what picture?
In one of the graphs of the conductance, you have conductance versus E in units of T.
Yes.
Is parameter changing the spin-orbit interaction?
No, it's not
Okay.
changing.
No, just to be sure that you are using always the lowest order in the expansion of the spin-orbit interaction. And you should be aware that if the energy is too high, you need to account for high order terms in the spin-orbit interaction terms. Well, you are just keeping the linear terms.
Okay, we don't have any account the changing of the interaction. Okay.
Okay.
Okay, thank you for your question, Dario. So let's move on now. Thank you, Hernan, for your talk.
You're welcome.
And so you can please take your presentation. Okay, good. So Dario, can you upload your presentation now?
Yeah.
So next talk will be given by Dario Berciu from the Donostia International Physics Center in San Sebastian, Spain. And his talk will be about abelian and not abelian geometric phases in transport through polygonal structures.
Yes, I'm on my way, sorry.
Okay.
Yeah. Can you see the presentation? Diego?
Yes,
can you see the
yes, I can see it, but you but it's not. You should. It's not in full screen. It's in rehearsal.
Oh, oops. Sorry. Let me try
now
like
you
this.
can do full screen.
Yes. Now it's.
It's not full screen yet. It's
now is it full screen?
No, it's rehearsal.
Okay, like this.
Now, yes, yes.
Okay. Sorry for this inconvenience. I did the test at home, but now I'm in the office. So thanks for giving me the opportunity to present the work that I'm doing in collaboration with one of the organizers, that is Diego, and with a former bachelor student, that is Alberto Ijano, and a postdoc in my group, that is Tineke Vandenberg. And the reason why I'm working on this is because many years ago, Diego proposed me to work on a set of a beautiful experiments that were conducted in the group of Professor Nita in Japan. And here I'm just briefly summarizing in these slides most of the results that we have seen in the first talk this morning. So we have the case where we studied the so-called ABC effect, as Klaus coined in the physics article appeared together with the PRL in 2012. So the idea is to combine the Aronoff-Bohm and the Aronoff-Kasher effect, and this is why it's going to the ABC. And later on, they started to work with the Aronoff-Kasher with the addition of the Zeeman term, and this is what I'm calling in this slide ABZ effect. So what we tried to do back then with Diego was to, instead of using a standard tight binding procedure for trying to address this physics, was to try to use a different type of approach that is based on the quantum graph technique. So now let me briefly introduce the idea of what is a quantum graph and why it can be useful for studying this kind of physics. Well, the idea is that a graph or a network is a set of vertices that are connected by edges. And now these vertices and these edges can describe something that is periodic or with any other type of structure that can be also a periodic or fractal. And so far, this is just a mathematical object. It's becoming an interesting object for physicists if now we associated an Hamiltonian to each one of the edges of this system. So roughly speaking, each edge will be described by a quantum wire. So now instead of what we're going to do is to solve this set of quantum wires by asking the Dirichlet boundary condition. So for each wire, we require that the wave function is fixed at the two extremes of the wire. So then we will have a set of wires that are all connected to each other. And we can solve this huge Hamiltonian operator that is given by the connection of all those wires, of all those edges, requiring the continuity of the wave function and the continuity of the current operator, so current conservation. And this will make so that the Hamiltonian of the quantum graph will be a self-adjoint operator. So we can find a unique solution for the spectrum. But now we want to do something more because we want to do this for, so we want to do this for transport. But before to show how to do this for transport, we should keep in mind how this would work for the case of the Aronoff-Bohm Aronoff-Kasher effect. So again, we will have a collection of wires that are connected to each other. And now the Hamiltonian for each generic wire will be simply the standard quadratic Hamiltonian plus the orbital part of the magnetic field for studying the Aronoff-Bohm effect, plus the spin orbit coupling of Rashba type corrected by the presence of the orbital term. And here I'm adding also the confinement of the wire that in principle I'm considering very strong so that I can consider single mode quantum wires. So a generic solution of this Hamiltonian with the Dirichlet boundary condition looks like this. So this is an Hamiltonian that is containing the Aronoff-Bohm phase, that is the standard Peierls transformation where we have the integral over the vector potential. Then there will be an SU2 terms that is describing the spin orbit coupling. And then we have this linear combination of those two signs that make such that the wave function is either one constant on one extreme or a different constant in the opposite extreme. And then the boundary condition for the overall network or graph reduced to this condition for those M coefficients that are nothing else than the constant that are present inside the wave function. But we want to go beyond simply studying the spectral properties. We want to study the transport properties. So we need to take an isolated graph or network, and we need to connect this with the external world. So we need to place contacts. So the simplest thing is to consider the case with two contacts, so a left and a right contact. And for example, we are injecting carriers from the left one into the system, and then we are collecting the transmitted one into the right one, and the reflected one clearly in the left one. And clearly, now we have to include an additional sort of wire that is going into the system, where we have the incoming wave that will be a spinor because we want to do spin resolved transport. and we will have an outgoing wire for the right lead that will be also described by a spinor, or still because we want to study transport, spin-dependent transport. And clearly now we are going to modify the boundary conditions that are moving from being homogeneous and are becoming inhomogeneous, because we are adding this term that is the incoming term inside the left lead. So we can find a unique solution that is giving us the reflection and transmission coefficients. And clearly, once we know all the T sigma prime sigma and RR prime sigma prime sigma, we can calculate the total transmission, the total reflection of the system. So we used this formalism back in 2006 with Diego in order to study transport into a set of regular polygons. And the idea was to see if a set of regular polygons that are containing a lot of vertices can describe the transport through a ring. And the easiest things that can be done is to study just the direct path, so the phase that electrons are gaining moving along the upper path moving between A and B, or between the lower path moving between A and B. And those are those two given here, where now those phases are accounting for the spin-orbit coupling or for the phase due to the orbital magnetic field. And then to the lowest order, the transmission of the system can be calculated simply as the trace of this gamma n0 operator. And this is the result that we get for the case of the square. So what is interesting here is that we see oscillations with a transmission that is going between a maximum of 2 and a minimum of 0 that corresponds to destructive interference. But actually the system is not yet as a strange periodicity, because we see that at the value of the spin orbit parameters of 4, we have a sort of plateau. And this is an effect associated to the presence of those vertices that are making the system not adiabatic. And by increasing the number of vertices of the system, attempting to approach the case of a ring, we see that this sort of plateau is shifted from 4 to 6. And if we move to an octagon, this is going to 8. And clearly, if the story is that if we make this larger and larger, for example, in the case of ring, this plateau is disappearing, but somehow the periodicity is approaching what has been calculated analytically by Klaus and Diego for the case of the ring, that is given by this expression of here down there, where for very large spin orbit coupling, the system is becoming adiabatic. So we can also go beyond just calculating the half phases, and we can calculate the full conductance of the system. Clearly, the result will be decreased compared to the case of 2, and is going to a value that is around 1.6 E square over H. But somehow these features with the plateau is still preserved also in the full conductance of the system. What we did lately was to upgrade those results of 2005 to include also the effect of the Aronoff-Bohm phase. And the result is summarized in this set of density plot, where we have the conductance of the system in units of 2 square over H versus the Aronoff-Bohm phase and the spin orbit coupling along the y-axis. And as we can see, again, we have this plateau that is related to oops, sorry. We have this plateau that is related to the non-adiabatic transport through the polygons, but as soon as we move to the ring, this plateau is moved so high up in spin orbit coupling parameter that this is disappearing from the plot.
So Rosario is in rehearsal.
Again, sorry. Now? Is now correct?
Now it's fine, yes.
Perfect. So now that the game is to include the effect of the Zeeman term. And what we did was to treat the Zeeman term as a time reversal breaking SU2 term inside our quantum wire. So now the Hamiltonian that is describing a single quantum wire is of this type. So we have so gamma is the generic direction of a wire. and alpha is the generic direction of the Zeeman term compared to the XY axis. So alpha and gamma are both the angles compared to the x-axis. And as we can see, we can now treat both the spin-orbit coupling and the Zeeman term both as SU2 terms, but only the spin-orbit coupling is depending on momentum. So this is the only one that is preserving time reversal symmetry. If we do like this, again, this is just what I told you right now. We can write now the wave function, the generic wave function, as still as a spinor, where now the phase of the spinor will be given by, will be the argument of a complex number that is accounting for the spin-orbit coupling and for the generic Zeeman term. The disadvantage now is that we cannot write anymore an elegant wave function with the Dirichlet boundary condition, but we have to account for the propagation of the spinor along the wire. So this can be done, is numerically achievable. And thanks to this wave function psi of gamma of R, we can now calculate the conductance also for the Aronoff-Kasher plus Zeeman case. So those are the results for the case of the square, that it looks very similar to what we have seen in the presentation of Professor Nita this morning. Then we have the cases where we are increasing the number of vertices, and we see that the number of minima, that are those black regions, are increasing up to reach the case of the ring, where we have this sort of semi-spherical or a quarter of spherical trace of minimal conductance, while when the Zeeman is dominating, the destructive interference is neglected. And this is the result that we've seen in the first talk today. So we see that our method somehow is in agreement with the experiment and also with the perturbative method that was worked out by Diego and his collaborators. With the difference is that and then in the more recent work by Diego and Professor Nita, where they studied the case of a ring and squares. So this is the case of the numerical collection by Diego, where they just consider the time reverse paths. And we see that in this case, the results that are obtained with this method with time reverse paths, this is quite different compared to the case that we are getting here with the quantum networks. The reason is that we are considering all the possible paths inside those closed geometry, while with the time reverse path, this is just a subclass of those. What we can do, we can introduce disorder inside the system, and in order to try to mimic those results obtained with only the time reverse paths. And the way in which we introduce disorder is by considering random fluctuations of the wire length by keeping the perimeters of each polygon constant. And this is a model that somehow worked. Indeed, we are able to in the case of a magnetic field flux, we recover the AES oscillations, and we have also a similar effect in the case of spin-orbit coupling. So now here I'm presenting the result for the ABC case for the square on the upper row and for the ring in the lower row. And as you can see, for the case of the square, you see also for a very small disorder that there is a doubling of the periodicity of the conductance with respect to the spin-orbit coupling with respect to the flux. However, for the case of the ring, the doubling of the periodicity for the smallest of the strength of disorder we consider is not really visible. We need to increase the strength of disorder to start to see this effect. This is actually more visible. The physics looks nicer in the case of the Aronoff-Kasher plus Zeeman, where you can see that now the feature looks very similar to what has been calculated by Diego just by considering only the time reverse paths. So now you see that the features looks similar to the case calculated by Diego, already with a disorder strength that is of the order of 10%. What we did more was to start to look at what is happening when we change the direction of the magnetic field with respect to the sides of the square polygon. We had in the first talk this morning that a lot of physics can rise up if we started to rotate the direction of the magnetic field. And what we find quite interesting is that in the case of the square, if the magnetic field is parallel to one of the wires of the square, is that if we move along the line in which the Zeeman term is equal to the Rashba term, when the magnetic field is parallel to the contacts, along this middle line of the plot, we see that the conductance is oscillating a lot. While when we rotate the direction of the magnetic field, we can see that the conductance is smoother. And we find this quite interesting, and somehow we can connect this to the physics of the helix of system in the presence of Rashba and Dresselhaus term. And the reason is illustrated in the following slide. So again, now I'm presenting result for the square in the case we consider several directions of the magnetic field. And as I told you, when the direction is parallel to one of the wire, we have this green trace that is quite regular compared to all the other cases. And we can interpret these results in the following way. So in principle, the most important paths inside the square are the direct paths. So something moving on the upper path or on the lower path, or something moving with time reverse clockwise or time reverse anti-clockwise. So the direction of the effective magnetic field due to spin orbit coupling are those purple lines. Now the question is what...
Sorry, you have 5 minutes left.
Yes, thank you. So now the question is what is happening when we add also the magnetic field parallel to the wires itself? So what we see is that in the case of the direct paths, two of the contributions are completely cancelled. So we have two wires along which there is not anymore a spin precession when the electron is propagating along those wires. And something similar is happening in only one of the wires for the two time reverse paths. So this means that introducing disorder is not enough to cancel this effect of this kind of pseudo helix effect. As we can see in this, in the case of this plot, where is conductance for various angles as a function of the Rashba term along this line in which the Rashba is equal to the Zeeman, we see still that for 45 degrees, so the green trace, this is quite more regular compared to all the other traces. Last things that we did was to check that our quantum network method is giving results that are compatible with wires of finite size. So for this, we used Quant, and we did a tight binding analysis of system with a finite width. And what you can see from this slide is that both for the ABC case or for the ACZ case, that the results are quite in agreement. I'm presenting results only for the square and the ring because those are the cases that are more relevant for the experimental case. And with this, I'm reaching my conclusion. And during this talk, I presented you an alternative method based on quantum graph approach for studying transport and in the presence of magnetic fields, so U1 fields or SU2 fields that are either time reversal conserving or time reversal, or that are breaking time reversal symmetry. And I use this for studying the transport through polygonal structure where I want to study effect of interference. And what we are working around right now is how this method can be used for studying a sort of topological phase transition in the presence of modulation of Rashba and Dresselhaus spin orbit coupling. And with this, I want to thank you for your attention.
Thank you very much, Dario, for your talk. So now we are open for questions, please. Any questions? You can just open your microphone. No questions there?
It's Carmine. I would have a question for Dario. Yeah. So Dario, probably I just missed the point. So your quantum graph approach can be generalized also to system with many modes, like 5 modes, 6 modes, or it's like designed for really one-dimensional settings?
In principle, it's designed for one-dimensional modes, but you can change the sorry, is here. You can change this condition for the current conservation. You see this lambda factor?
Yeah.
So you can work on that, and you can make an effective theory for describing a sort of many modes systems.
I see.
So you work with a single mode, but by changing this current conservation condition, you can simulate many mode systems. So basically, you're introducing best scattering between the modes.
All right. Okay. Thank you very much, Dario.
Welcome.
So related to the Carmine's question, so you can mix, with this model, you can mix the modes at the nodes.
Yes, exactly.
It's not during propagation along.
No, in principle, you know that spin orbit coupling, it allows you to mix the modes, the Rashba spin orbit coupling, if you have a system of a finite size.
Yeah.
But I would not know how to do this in terms of a quantum graph approach.
Okay. Another interesting application, I assume, is to study complex networks. Which is...
Yeah, indeed. The advantage is that you can easily study the type of networks that we saw in the first talk without the complexity and the ethical numerical machine of doing tight binding discretization.
Okay, thank you very much, Dario, for your talk. So let's go on with the program. Next talk is by Anton Ramsak. Are you there, Anton? Tony?
Oh, hi.
Good. Okay, can you upload your presentation?
Okay.
Good. So the next talk is by Anton Ramsak from Ljubljana University in Slovenia. And his talk is about effects of environment to the generation of quantum phases. So please, Tony.
Okay, thank you, Diego. And thank you, the organizers, for the talk. I try to visit Madrid every year, my friends in Autonoma and Complutense, and I'm really glad to be able to present my work. So I will talk about the effects of environment to quantum phases. So my collaborators worked on this problem with me for the last few years. And first I will just present our special system where we found an exact solution for it. And that's very useful, maybe also for somebody else. And then with this model, one can exactly treat quantum phases, various quantum phases. And then in the last year, we succeeded to solve this problem of coupling to the thermal baths. And this is the main thing, actually, the main result. So the idea is to manipulate qubits, which are spins of single electrons, and in solid state devices of different types. Of course, the main, our goal is to study all this without magnetic field like we do today, so with the Rashba interaction. So what we need is actually dependent Rashba interaction. So imagine some system where with the external electric field, we change the Rashba coupling. So this is one old example when one can change the strength, the Rashba strength for a factor of 2 with the external electric field. There is, one can do even more than that, which is in this example, more recent, when one can change in a quantum nanowire along this direction, the strength of Rashba interaction by factor up to 6. So we assume that somehow we can manipulate size of Rashba arbitrarily. So this is one ingredient which we will need in our approach. Then imagine now that we have one-dimensional system. So two-dimensional electron gas, we have one-dimensional confinement along these lines. We have electron here, and we can move this electron left, right. So imagine that this electron is actually trapped in a parabolic potential, and which can move along this direction x. And on top of that, we have external or additional Rashba interaction, which is manipulated by external homogeneous electric field. So in our model, we have then electron trapped in one dimension, where position of this trap labeled with psi can be arbitrarily changed, left, right. So our model is actually this, very simple, harmonic oscillator for electron moving along this line with time-dependent position, which we control. And then on top of this, we have the Rajba term, where we can tune the Rajba interaction arbitrarily. So we have in our system two parameters. We all know this old problem of the Berry phase, when you have two parameters and you do some adiabatic transitions of your Hamiltonian, you can acquire some quantum phase. So this is the essence of our work, but we go much further. So what is interesting is that this problem can be solved exactly. Of course, in this short presentation, I'm not attempting to present the derivation, but just remember, we have harmonic oscillator, we can move it left, right, electron is trapped there. We can change the Rajba, and this was solved many years ago actually by Kodich Husimi for this part. We added exact solution also of this part. This is no big deal because actually these degrees of freedom are independent because of this spin variable, and we can treat also this part using the same method of Kodich Husimi. So this is actually some kind of canonical transformation which transforms this original Hamiltonian to a time-independent and spin-independent form. So we presented this in last year in several papers. But the main ingredient of this transformation is actually solving completely classical equation of motion. So imagine this left-right motion of the harmonic oscillator as this first equation. Xc is classical solution to the driving psi of our problem. So we drive our system with psi, quantum system, but first what we have to do is to solve classical analog. And the same has to be done with the Rajba term. So we drive Rajba system and we need classical AC response to this driving. So these two classical variables, numbers, functions are needed. And then once we have this, then we can generate canonical transformations. So some unitary transformations which incorporate these classical solutions. And we get some kind of coherent state which moves left, right, and rotates in the Rajba or in the spin space according to classical equations. So it's quite interesting, but of course we don't have time here to discuss the details. So once we find all this and check, we can prove that using this transformation, so all this together, will, if this is U, if I denote this as kind of unitary transformation, we can map or change this original time-dependent, spin-dependent Hamiltonian to time-independent, spin-independent H0, which is just simple static harmonic oscillator. But all the secret of the exact solution is, of course, hidden in this unitary transformation. Now, this is all interesting, but for the purpose of today's section, we need quantum phases. So if we check this transformation, we see that what we get is some kind of scalar phase and additional phase which corresponds to spin rotation of our spin system, of the electron, of this trapped electron. And then there are additional terms. So it is quite easy to show that we can get rid of these two unitary terms if we do such transformations that we start with spin and electron in some eigenstate of the harmonic oscillator, make some kind of transformation. At the end of the transformation, we can, if we move it in such a way that the electron will not move left, right, and will stay still after the transformation in the classical case, so this Xc and AC return to the initial value, then these two operators are identity. So all what we get in this case is actually just this spin rotation and additional quantum phase. So with this, then we can study quantum, quantum phases. So I will just briefly mention. So classical Henny phase, of course, we know, and then Pancharatman and the Berry phase, which is most famous. This is for systems where we move Hamiltonian parameters adiabatically, and we get only one scalar. This is just standard phase. Then Wilczek-Z generalization of this was case when we could have, for instance, spin rotation, like this case. So we have quantum phase, which in this case is spin rotation. This could be also more dimensional than 2. So this is phase development was Aharonov-Anandan phase, which was non-adiabatic but scalar. This is generalization of the Berry phase, where we can move or change parameters non-adiabatically. Okay, we go further. The last step or stop in our approach is this Anandan phase, where we do transformations of parameters non-adiabatic, but we can rotate spin. So this is what we need actually today. So in our case, our solution gives very simple results. So if we move our system in the space of parameters, so remember, this is position of the Hamiltonian, alpha is the Rajba. If we make one circle, for instance, or some closed loop in the parametric space, then the area of this would be somehow like the Berry phase if we would study non-degenerate case. But in our case, we have degenerate system, we have spin, which will be rotated through this term. So our transformation will take this form. And what turns out is that actually the area of this red curve, which is the area in the space of response to the Rajba interaction and driving to the position. So this area is actually exactly the angle of spin rotation for this system. And this we found 3 years ago. And now what we are interested in today is how the environment changes in this solution. Here I just give some experimental example. One can really make angles of the order of 1 radian for typical values which are achievable. So this is really doable. Then let me just mention standard phases. If we would do this transformation adiabatically, this would mean that the response of the position would be just the position of the trap, and the Rajba response would be just the Rajba value. Then this area would be adiabatic contour, and this would give the Wilczek-Z result for this problem. So if we would drive very slowly, we could get this. The Berry phase would be if we would eliminate degeneracy. This again would give the same type of result. And the Anandan phase is what we have. We can analytically again express all terms which are needed for this separation, in this case for dynamic and geometric part, and all these different combinations of responses and drivings and areas in these spaces give the phase. This is just repeating of our old work. Now I'm coming to the main part of my talk and to the end, basically due to the time limited. This is now coupling of this system to the environment. So we took very simple coupling. We took just some kind of dipole interaction with some fictitious or some bosonic field. So we have some bosons, could be some phonons or electromagnetic or something, and we couple position relative to the center of the trap to this environment. So this coupling could be also in some different form. This is one example. So if it is so, then our total Hamiltonian is just our system, S now, known from before, our bus, internal equilibrium, some temperature and coupling. So coupling is again time dependent, and it comes through this term. So this is now new from this year. So what one can do then, because we have unitary transformation which solves exactly the original problem, we can do most of the work analytically. Of course, here I cannot go into the details, so we use our unitary transformation. then do the first order. So the system is not effective, so perturbative way. The Markov approximation, so no memory. The second order, and what we end up, no surprise, with the Lindblad equation. Of course, this is the main or the most useful equation in this lowest order. But what is nice in our problem is that we get all these operators exactly or directly because we have all unitary time development of the original system. So everything can be done very, very far analytically. So what we get is relatively simple, actually. So the density matrix of the system, of our qubit system now coupled to this thermal bus, we have three terms. One is some kind of lamp shape operator, which is non-trivial. It is again spin dependent and many terms. It's quite non-trivial. And then we have coupling to the spin part, just sigma. So one Lindblad operator is sigma y. Here we took for convenience just one direction, sigma y. It could be more general, of course. And then there is another term which is also interesting, is this damping, which is of course expected, and spin together. So these coefficients are Fourier components of the driving. So don't forget, we drive our system non-adiabatically, and our driving function, which is arbitrary in principle, is composed of different Fourier components, and all these classical responses then generate Lindblad operators. And then we have these standard terms of the Lindblad equation. So let's go to the results. I guess that I have 5 minutes. Do I have, Diego?
Yes, exactly.
Yeah.
I was about to tell you. Yeah, you have 5 minutes.
I'm trying to come to the main thing. So imagine now our space of parameters. We have position. Our electron is moved left, right within the trap, and we change the Rajba interaction. So we drive the system along this circle. This means along this circle, we drive parameters. But the system, because this is non-adiabatic, responds say along this black line. So this black line is a response of the system. And if there would be no interaction, so G equal to 0, the area of this full black line would be the angle of rotation. One can express this also in terms of the other pair. There are different pairs of coordinates. So for now, just concentrate to this full black line. So the area of this loop is rotation of spins. This is the Anandan angle. Now, if we add the interaction, the path will not be closed loop anymore. This is the main effect. So what we see after one circle, that we end up at some other position. So this is the effect of this kind of environment. So on the Bloch sphere, if we rotate around the vector n, spin initially up. Here I chose full spin flip after two cycles. So we make the spin rotation. So all these wiggles are simply due to driving of the system and the response, which is non-trivial. But now if I add the interaction, I get these red dots. The first effect which I see is spin is reduced. So I get some, so the spin is lost during this dissipation process, and angle of spin is not precisely pi anymore. So we have mainly analytical results, just the final steps are done numerically in Q-tip formalism. So this is one example how the driving changes. So we drive the system. If there would be no damping, we would have this black line periodic oscillation of driven oscillator, but due to the environment, we get this shift. And on the right, we see several cycles. We see that maximum changes. Interesting is that if we take a completely classical damped oscillator, we get very, very similar effects. So with this, we can see that our Lindblad formalism is actually quite reliable, very similar to classical viscous damping. It's not the same, but very similar. Then what happens with spin? during the driving spin oscillates because of the Rajba, but if there is no damping, is this black line. So we start here. This is time dependent of size of spin. It is never fully 1 because it's the expectation value of spin, but we have this Rajba, this Wigner states. So we have spin starts with maximum value, it goes down and returns. If we have interaction, it does not return anymore. So it slowly decreases. So if I make more circles, so this was 1 loop, if I make more and more, what I see is that this loops after some time stabilize. Again, we can understand it. This is like classical driven oscillator, but damped. When we start driving, it will oscillate because we have also this homogeneous equation solution, but after some time, due to damping, it damps out. And what we end up is just the response to the driving. So this is another example. So we should check this red curve. So this is after few cycles, but after many cycles, we get this limiting cycle, which means we drive the system. This intermediate transition period is over. We again get a perfectly periodic solution. And now we can ask about the phase. Originally, the phase was just the area of this, but of course, in this case, this is not true anymore because the loop is not closed. So we can check the error of the phase. This deviation from pi, in this case, we can see that with number of cycles, first we have some oscillations. This is just, from this we see that we have damped oscillator, but after a very long time, all these oscillations are damped out. And then the phase, this is for different coupling strengths here, the phase increases with time monotonously. The reason is that we have then monotonous dissipation of phase, so to say, while the oscillation in the position becomes steady, just a response. And the similar is with the size of spin. So gamma is, so size of spin is defined by this formula. So if gamma is 0, we have spin 1 or constant initial value, but with time, this gamma increases. Also, size of spin is reduced. So after many, many cycles in this block sphere, we would end up in the center. So with this, I'm coming to the results. So our unitary transformation, which without these red squares or blocks is a non-interacting case. What we see, we have phi, which is an unknown angle corresponding to the rotation of spin in our case. So if we add interaction, we get error in spin rotation and we get error in size of spin. So this is a real gamma, this is real phi and I here. So we see that our unitary transformation now changes into this form, some kind of damping of spin size and error production in the phi. And what is interesting, again, this error in phi consists of two terms, of something which we could call dynamical part and something which is geometric. The geometric part is actually change of the area in the parametric space. And this, after a very long time, becomes constant because the damping is damps the eigen oscillations and we get just constant geometric term. And dynamical part we could call is term which is proportional with time and the interaction squared. We are in the second order of perturbation. And this is for the error of spin. And the same happens with the spin size, or this gamma, the measure of spin size. Again, we have some geometric part, constant term, and time dependent, which is linear. If I return this, so we have different time dependencies, but if we study this, we see that there is some fixed constant term, which we would call geometric error, and dynamical part, which is with time increasing error. And with this, I came to the end of my analysis. So first part was introduction. We have some system which is exactly solvable. For all different phases, I showed only one example. And we showed that one can couple this very easily to thermal baths of different types can be, and one can very nicely study this system. And with this, I finished. So thank you very much.
Thank you very much, Tony, for your talk. Well, we may have time for one brief question. Anyone?
Hi.
Yes.
Hello.
Who's that?
Hi, it's me, Adrian. Thank
okay,
you.
Adrian. Okay.
Thank you very much for your talk. I would like to make a question about the possibility of trying to know more about the quantum chaos within this kind of experiments. What do you think?
I have to say that this is single electron case, and the interaction is just with bosonic environment. So I would not expect any chaotic behavior here, but maybe I'm wrong.
Okay, thank you very much.
Okay, so I have one single comment, Tony. So in your introduction, when you define your parabolic potential and the modulation of the Rasch-Spinor recoupling, can you go to that slide, please? Yeah, I think the next one. Okay, this looks like a transport configuration, right?
This I took from some paper where maybe one should not consider this. This is just
okay. I thought I was considering that seriously. So maybe is that maybe it looks like a pumping. I mean, the protocol you introduced may work for pumping between electrodes.
No, well, no. This you should consider only this Hamiltonian. So it is really parabolic potential where electron is trapped. So it will not move far because it is in the parabola. It is trapped, or maybe in this. So you should consider this part. So
okay.
Electron is trapped. So these gates here are not gates really. This goes forever up.
Okay, no, because maybe if you are able to couple that to contacts and just performing this cycle in the parametric space, you could perform some pumping.
Yeah,
pumping or something like that.
Of course, in our case, the main thing for this kind of analysis is that this is a harmonic oscillator, and this is why it is solvable. And that's the main beauty. You can study all features basically exactly because this is so simple. This is just harmonic oscillator.
Okay, I thought maybe it's possible to apply this to pumping with dissipation, with coupling to the environment.
Yeah, that maybe.
That would be a possibility, I think. Okay, thank you very much.
Thank you to everybody
for your talk. So let's move on. We have a little delay, not much, I think. So, and the next talk will be given by Beatriz Perez. Beatriz, are you there?
Here I am.
Okay. So the next talk is by Beatriz Perez from the Institute of Material Science in Madrid. And her talk will be about simulation of chiral topological phases in driven quantum dot arrays.
So thank you for the introduction. I'm sorry I cannot turn my camera on, but it's not working today for some reason. Anyway, this is me, and today I'll be talking about simulation of one-dimensional topological phases in driven quantum dot arrays. For further details, you can check the two references that I leave here. And to begin with, in just a few words, this talk is about how to use quantum dot arrays as quantum simulators for topological phases using time-dependent modulations. So let me call your attention on these two papers by two different experimental groups in which they demonstrate fully controllable long quantum dot arrays. So this achievement has opened up the possibility of using this solid state platform as a quantum simulator. This is the Hamiltonian that we will be working with. The first term corresponds to all the couplings between quantum dots. Note that we have included long range hoppings up to range capital R. So this maximum hopping range is determined by how the hopping amplitudes decay with distance. Though small, long-range hopping amplitudes may have a non-zero value depending on how the electronic wave functions overlap. The second term in our Hamiltonian corresponds to the driving field. It comprises a time-dependent periodic function which modulates the amplitudes of the field on each side. So for our purposes, we choose this time function to be a square pulse. In a more visual way, this means that in the first half of the driving period, we have a certain configuration of the field amplitudes, and in the second half of the period, this configuration changes sign. So in the high frequency regime, in which the frequency of the driving field is much larger than any other energy scale in the system, we can describe our time-dependent system through an effective time-independent Hamiltonian with renormalized hopping amplitudes. And this is the renormalization that we get based on the time dependence that we have chosen. There are two important things to mention about this function. The first one is that it depends on the difference between the on-site amplitudes of the driving field. And the second one is that it has periodically spaced roots located at those values of the difference that make the exponential go to 1. So which are the systems that we aim to simulate with this driving protocol? Well, a canonical example of such Hamiltonians is the SSH model, which is a dimer chain with alternating first neighbor couplings. So despite its simplicity, this system hosts two topologically distinct phases depending on how we choose the value of the hopping amplitudes. We can see that by plotting the energy spectrum as a function of one of those hopping amplitudes. We can identify two distinct topological phases, and the one with non-trivial topological features is characterized by the presence of two edge states within the gap at zero energy that are maximally localized at the ends of the chain and that are topologically protected against local perturbations. Also, we can label each phase by a quantity named topological invariant, whose value is directly related to the number of pairs of edge states within the gap. We can think of other examples as well, but what they all have in common is that they have periodically modulated hopping amplitudes, whose value determines the topological properties of the system. Topology manifests itself in the presence of edge states within the gap, and those edge states are protected by the presence of a certain key symmetry, which in the case of the dimer chain is chiral symmetry. So, well, so far what we have is a monomer array of quantum dots with long-range hopping. And we assume that in this type of setups, we would expect these undriven hopping amplitudes to decay exponentially with distance. So our statement here is that with our driving protocol, we can recreate any spatial pattern of interest for the hopping amplitudes. At the same time, we can imprint certain key symmetries that provide for topological protection, and that this control and tunability of hoppings happens from short range ones to arbitrarily long range ones. So in order to illustrate how all these features come into play together, we are going to simulate a particular system, which is the extended SSH model. We have already talked about the standard SSH model with first neighbor couplings. So now we wonder what happens when we add long range hoppings to this system. We find that there is a crucial difference between adding even neighbor hoppings and odd neighbor hoppings. On one hand, even neighbor hoppings always connect sites belonging to the same sublattice. So chiral symmetry is broken and topological protection is lost. So these are processes that we do not want in our system. On the other hand, odd neighbor hoppings always connect sites belonging to the same sublattice. They preserve all the fundamental symmetries of the system, including chiral symmetry. And what's more, for certain values of these Hoping amplitudes, we can get configurations with a larger value of the topological invariant, which translates into more edge states within the gap of our system. So something to mention about these S-trappers of edge states. Consider a configuration with first and third neighbor hoppings, no second neighbor hoppings. We would get at most 2 pairs of edge states, and the extra pairs are not maximally localized at the ending sides of the chain, but at inner sides. Well, so how do we set the parameters of our driving protocol to simulate this particular Hamiltonian? So the first thing we need is to recreate the dimer structure. And for doing so, we choose the on-site amplitudes, the difference between adjacent on-site amplitudes, to recreate this stair-like pattern following an alternating difference. So we get this alpha, beta pattern, and so on. Recall that the renormalization function depends on the difference between the field amplitudes on each side. So by choosing the field amplitudes in this way, we make sure that our odd neighbor hoppings will always renormalize following an alternating pattern. So we also want to suppress all even hoppings at once. So even neighbor hoppings will always renormalize through a multiple of the sum alpha plus beta. So we make this sum coincide with one of the zeros of the renormalization function. And that's it. In the high frequency regime, we would get an effective dimer structure with alternating odd hoppings and no even hoppings. This is the topological phase map that we get as a function of the field amplitude alpha. Remember that beta is fixed, but if we want to suppress all even hoppings at once, and also as a function of the decay length lambda of the undriven hopping amplitudes, assuming that there is an exponential decay with distance. Each color in the plot represents a different topological phase with different topological invariants. So as you can see, we can virtually have access to topological phases with a very large topological invariant. An important detail about this calculation is that the maximum range of the hopping amplitudes included is defined as a function of lambda in this particular way. So now we wonder about the implementation of this protocol in a short array of 12 quantum dots. We set our hopping amplitude so that we have first to third neighbor hoppings, and then we plot the energy spectrum of the driven system as a function of the field amplitude alpha. So by modifying the field amplitude, we can see how we can transition from a trivial phase to non-trivial topology phases, and eventually to configurations with 4 edge states, as you can see in the inset of the plot. To conclude, we have also studied the dynamics of particles with opposite spin that are loaded into the system. So this could be used as a way to prove the topological properties of the driven system, since when a particle occupies an edge state, it displays oscillations between those sides with maximum probability. We have numerically simulated the exact dynamics also to check all the analytical results that I've presented so far. So we consider here 2 particles with opposite spin loaded into the system such that the first one occupies the first side and the second one occupies the third side. And then we choose for our simulation the parameters of the driving field so that we get 4 edge states in our system, and also to meet the high frequency regime. What I plot here is the occupation of the chain for each particle for the case in which there is no interaction between them. And what we see is that they display independent, coherent oscillations between different sides of the chain. The frequency is determined by the energy splitting of the pair of edge states. So when we turn on the interaction, we see that the particles exchange spectral weight and their dynamics gets correlated. But importantly, the edge states remain well isolated from the bulk, so the intermediate region is not populated by the particles. So this is the end of the talk. Here I leave my conclusions, and thank you for your attention.
Thank you very much, Beatriz, for your talk. So we have time for questions. So please, if there's any, you can just open your microphone and ask.
Hi, Beatriz.
Hello.
Who's there?
Hi,
Adrian?
it's me, Adrian.
Yeah,
Thank you for your talk. I would like to ask you a question about the possible use of these devices as filters in order to filter some frequencies from in a system, from perhaps some signal or so.
Filter, I am not very familiar with filters, so if you could expand your
Yes,
comment.
of course. Imagine you can try to select some frequencies, for instance, from in a quantum system, and then you are trying to design a quantum gate or so. So is it possible to imagine the use of these devices as such kind of way of filtering this?
Well, you could set your driving parameters so that the particles that you load into the system display oscillations in the frequency you want to have.
Okay.
If that answers your question.
Yes. Yes, I think so. Thank you so much.
So, any other questions? Beatriz, I would like to ask you a question about the experimental implementations, because here in your final slides you comment about protocol could be implemented in other platforms or to the system. What do you have in mind?
Well, to the arrays of quantum dots, so that you could get not edge states, but surface states or corner states, edge states.
Okay, could it also be implemented in, for instance, systems of collaptons where you have very good control of the local
Yeah, sure.
and non-local control? Yeah, okay. Any other questions? If not, okay, let's thank all the speakers again. Thank you very much for participating of this. Please stay online if you like to take part of the collective